Hello everyone, we are Group 21. I am Nathanael Setiorahardjo and my partner today is Gavinn Aloys. And today we are presenting our research on curing the data hunger problem in vision transformers using a method we call inductive bias warming via progressive attention. So our research paper is titled Thinking Inside the Box, Progressive Window Expansion for Data Efficient Vision Transformers.
Okay, to start off, what is a vision transformer? Think of it like a jigsaw puzzle. A standard vision transformer looks at an image by breaking it into small puzzle pieces or patches. But unlike older models, it tries to look at every single piece at the exact same time. So, as you can imagine, this can get very messy.
Before we go deeper into our discussion, let's know a little something about vision transformers and its properties. The problem is, VITs completely lack a built-in spatial inductive bias. Because of this, they are notoriously data hungry. And in low data settings, they struggle to learn basic features early on and become highly brittle. So we propose a solution called inductive bias warming, a parameter-free training curriculum for VITs. So it enforces strict local attention windows early in training, and these windows progressively expand to full global attention as learning stabilizes. This matters because it allows the VIT to learn spatial structure in the correct developmental order. It boosts accuracy, and it achieves this without adding any learnable parameters or permanently altering the whole architecture. So, as we can see here, so VITs, they can look at the house at the bottom left and instantly connect it to the sun in the top right. The problem is they completely lack a built-in spatial bias because they look at everything all at once. They are notoriously data hungry, so if we don't give them the massive amounts of data that they need, they struggle to even learn a basic edge or texture is, making them very highly brittle. So this is the visualization of how a VIT actually sees the images. However, using a VIT, it enables computer vision to be processed somewhat like NLP. Here, as we can see here in the self-attention part, so self-attention is a mathematical mechanism that calculates context by weighing the relationship weights between all words in a single sequence. So what does this mean? This means that one patch, so every patch is now correlated with each other, and the VIT can actually understand it more like a sentence rather than like an image.
Okay, to understand this problem further, I want you guys to imagine a confused explorer. So if you give a child a giant map of the world and ask them to find their own house, they'll get overwhelmed. This is what we call information overload. And that is exactly what happens to a vision transformer. To see the world, the model must first learn to see its own street.
Other researchers have tried to fix this using hybrid architectures. So basically, this means permanently stitching standard convolutions onto the transformer. But doing this destroys the purity of the architecture itself. It adds heavy structural baggage, messes with the hardware efficiency, and permanently limits the model's ability to do global reasoning later on.
So our solution is much simpler than that. We call it inductive bias warming. Think of it like a training wheels on a bicycle. You don't teach a toddler to ride a bike by pushing them down a mountain, do we? Yes. First you give them support, and then slowly take the wheels off. For our model, we start local. Then we force it to look only at neighboring patches. Then, as the model gets smarter, we slowly relax those limits until it can finally take a look at the whole global picture.
So mechanically, we achieve this by injecting a time-dependent constraint into the self-attention formula. So instead of a sliding mask, we use a physical window partitioning. This is critical because it gives us zero architectural changes, so meaning no extra trainable parameters, and drops our computational complexity from O of n squared down to O of n times W squared.
Alright, so here's how the training wheels work in action. In phase 1, starting from epoch 0 to 14, we use a fairly strict 2x2 window. The model is forced to learn basic local shapes. Then in phase 2, starting from epoch 15 to 29, we expand the window to 4x4. Now we're relaxing the limits. And finally in phase 3, from epoch 30 onward, we unlock the full 8x8 global attention. Now the training wheels are off, and the model can see everything.
Results. So the results prove that this curriculum actually works. On the full Sci-Fi 100 dataset, our progressive warming vision transformer achieved a peak accuracy of 66.81%, which is a solid 1.75% gain over the standard baseline that we used. Looking at the graph on this slide, you can see our model starts slightly slower during the restricted phases, which is by design, but then sharply overtakes the baseline once global attention is unlocked. But the real breakthrough happens when data is scarce. We start the models by giving them only 10% of the dataset, and standard VITs usually overfit and just memorize the noise. But because our model was forced to learn structural features first, our accuracy jumped double to a plus 3.42% gain. This proves our method acts as a true structural regularizer. As we can see, to avoid coincidence, we also performed an ablation study to prove our dynamic schedule is the reason for success. So we ran an ablation study. So we locked the window permanently to 2x2 or 4x4. Then, according to our results, it actually hurts the performance. The progressive expansion is mandatory. We also compared our physical windows to a sliding Chebyshev distance mask. While the sliding mask works in theory, as you can see here in this table, it explodes to nearly 4.3 billion operations at higher resolutions compared to ours, as we can see here in our table. So our proposed method helps keep these operations lean at roughly 4.1 million, proving that it is also a scalable choice.
So, most of you guys might have wondered, why does ACT research even matter in the first place? Alright, let me bring it up for you. So first, zero overhead. We did not add any extra weights. Second, pure architecture. We did not use messy, permanent Frankenstein layers. And finally, the third, high scalability. We make the early training phases faster and much cheaper to run. And that brings us to the end of our presentation. Thank you for listening.